So the first part of your homework was just definitions. I've written them all out for you here. You'll notice in all my definitions, I've used the word molecule. If you've used the word compound, that is absolutely fine. You can swap the word molecule for the word compound. I'm just going to go through a few of them. Hydrocarbon, I think everyone got this right in the test anyway, but just make sure that you're using the word only. Molecules that contain carbon and hydrogen only. For saturated and unsaturated, if it's saturated, you've only got single bonds between carbon atoms. Unsaturated, at least one double or triple bond. Just to clarify something else, when we're talking about the double and triple bonds, it has to be between carbon atoms. If I look here, I've got saturated and unsaturated fatty acids. You can see in your saturated fatty acids that you do have a double bond, but it's a carbon-oxygen double bond, therefore it is still saturated. In order to be unsaturated, it has to have at least one carbon-carbon double or triple bond. You can see here that I've got a carbon-carbon double bond. Here I've got 2 carbons double bonds. Here I've got 3 carbon-carbon double bonds. Okay, so the carbon-oxygen double bond does not make it unsaturated. It has to be carbon-carbon double or triple bonds. If we go back and look at our definitions, the next one we've got aliphatic, alicyclic, aromatic. The main difference here, if it's aromatic, it has to have at least one benzene ring. If it doesn't have a benzene ring, then it's going to be aliphatic. If those carbons are arranged in a ring, then as well as being described as aliphatic, you can also describe it as alicyclic. And I'll go through some of these examples in section B. For a homologous series, you must say that the compounds have similar chemical properties, and you must say that the successive members differ by a CH2 group. Okay, you need both of those in your definition. And when you're talking about the similar properties, you have to say chemical. Physical properties are just not specifying is not good enough. It has to be chemical properties. So if I look at an homologous series, the alcohols would be an example. I've got ethanol, there's propanol, there's there's butanol. So they've all got similar chemical properties. That means that your alcohols all react in the same way. And then the successive members, ethanol to propanol to butanol, the only difference between them is you're adding an extra CH2 each time. So they're all part of the same homologous series. Functional group, okay, the reason that the alcohols all react in the same way, the reason they've got the same chemical properties is because they've all got the same functional group, and the functional group here would be the OH group. Okay, that's what's common to all alcohols. That's the reason they have the same chemical properties. So if you're asked about functional group, you have to specify that it's chemical properties you're talking about, not just properties in general and not physical properties. Looking at structural isomers, molecules, same molecular formula, different structural formula. Homolystic and heterolytic fission. In each case, fission is the breaking of a covalent bond. We know that a covalent bond is a pair of electrons. So if I've got a covalent bond there between 2 chlorine atoms, if that bond breaks by homolytic fission, then each atom will take 1 electron from that shared pair and you will form a radical. If a covalent bond breaks by heterolytic fission, then 1 atom will take both electrons from the covalent bond. Because in this case chlorine gets its own electron back and gets hydrogen's electron, it ends up with a negative charge. Hydrogen loses a share of chlorine's electron and loses its own electron, so it ends up with a positive charge. So by homolytic fission, you're getting what we call radicals. By heterolytic fission, you're getting ions. When you're talking about homolytic and heterolytic fission, you have to specify that it's a covalent bond. So someplace in your definition, don't just say the breaking of a bond, specify that it is a covalent bond that is being broken. Radical, I've got a picture of a radical here above. It's a reactive species with an unpaired electron. So radicals will always be reactive. You don't need that in your definition. If you just said it was an atom or a group of atoms with an unpaired electron, then that is fine. Curly arrow, the movement of a pair of electrons. If you don't specify pair, you're not going to get the marks. So here, when I'm showing the breaking by heterolytic fission, I could draw a curly arrow starting at the covalent bond, which is where I find my pair of electrons, and ending at the chlorine, because the electrons move from that covalent bond to the chlorine to form a chlorine ion. So it's the movement of a pair of electrons. An electrophile is something that is poor in electrons. It's usually positively charged or delta positive charge. And because they're electron poor, they will accept a pair of electrons. You can't just say electron acceptor, it has to be electron pair acceptor. Electrons are always going to move in pairs in all the mechanisms that we will look at. And a nucleophile, again, that's something that's electron rich. Because it's electron rich, we say it's an electron pair donor. Please make sure that you are familiar with all of these definitions. You could be asked to define, or you could just be asked to use these terms, which is what we're going to practice in section B. But definitions are really easy marks, and please ensure that you are not going to lose any marks on those definitions. The next part here in section B, I've just got a table that I asked you to complete. I want you to fill in the functional group and then tell me the name ending for that functional group. I've already done the first two for you. For an aldehyde, you are going to have a carbon double bond oxygen. This is called a carbonyl group. For a ketone, you're also going to have a carbon double bond oxygen, which is also called a carbonyl group. The difference between your aldehyde and your ketone is the aldehyde, you'll find your carbonyl group at the end of the chain, and in the ketone, you'll find your carbonyl group somewhere in the middle of your chain. The ending for an aldehyde is going to be Al. The ending for a ketone is going to be One. And the ending for your alcohol is going to be Ol. So I've got Ol, Al, and One. For the carboxylic acid, you've got a carbon double bonded to an oxygen, and that same carbon is also single bonded to an OH. This is no longer a carbonyl group. As soon as you put the OH on the carbon, you're going from a carbonyl group to a carboxyl group. Okay, so that's the name of the functional group in a carboxylic acid, a carboxyl functional group. And again, you're always going to find this functional group at the end of a chain because carbon already has 3 bonds to it, so it must be at the end of the chain. If you've got a carboxylic acid, it's going to end in oic acid. So moving on now to section B, this is where I ask you to apply the terms that we've defined in section A. So the following, which of the following are hydrocarbons? We said they should only contain carbon and hydrogen, which means A cannot be because it contains an oxygen. B is a hydrocarbon. It doesn't matter, it's got a benzene ring. If it's only got carbon and hydrogen, it's going to be a hydrocarbon. C's got a chlorine, so it's not. D only got carbon and hydrogen, so D is a hydrocarbon. Unsaturated, we said unsaturated must contain at least one carbon-carbon double or triple bond. Straight away in A, I can see I've got 2 carbon-carbon double bonds. In B, I've got a carbon-nitrogen double bond, but I've also got 2 carbon-carbon double bonds. That makes B unsaturated. If I look here at C, I've drawn it in structural formula, which is a little bit harder to see. So if I were you, I would draw this out in skeletal so that it's easier to see. I've got a CH3 going to a CH2, going to a CH2, going to CH3. There are no double bonds there, so it is not unsaturated. The last one, again, I've got it in structural formula. I've got a CH2 bonding to a CH, bonding to a CH3. CH2, CH3. The fact that this carbon here is only bonded to 1 hydrogen when it would normally be bonded to 2, and here you've only got it bonded to 2 hydrogens instead of 3, that tells me that I do have a double bond, and that means that it is indeed unsaturated. So 3 of the 4 there are going to be unsaturated for containing carbon-carbon double bonds. The next one, which of the following are aliphatic? We said they are aliphatic as long as they don't have a benzene ring. I'll just remind you what a benzene ring looks like. There are 2 ways that you can depict a benzene ring. You can either draw it with a 6-membered ring and a circle in the center, or you can draw the 6-membered ring with alternating double and single bonds. And it doesn't matter where on the ring you start your double bonds. So here I have my first double bond between carbon 1 and 2, but the next one I'm going to go start it here, then I have single, then I've got double, then I've got single, then I've got double. So it doesn't matter where you are starting those double bonds, but it has to go double, single, double, single, double, single. So alternating around the ring. You can also use a circle. So these all depict benzene rings. If the molecule has one of these structures in them, it is not aliphatic. So the first one does not, so it is aliphatic. You can see B, I do have these structures, it's not aliphatic. C, I've got 2 carbon-carbon double bonds, but it's not the same as what I've drawn above. That is not aromatic, it is aliphatic. And then D, I do have that benzene ring, so it is not going to be aliphatic, it's going to be aromatic. So these two are your aliphatic, these two are aromatic. Which of the following are alicyclic? Okay, to be alicyclic, again, cannot contain a benzene ring, and they have to be in a ring structure. So this is not a benzene ring, but it is a ring, therefore it's alicyclic. This, not a benzene ring, but it is a ring. I know it's got an oxygen in there, but it's still a ring, so it's going to be alicyclic. Here, this is a benzene ring, so it's not alicyclic, it's just called aromatic. Here, you don't have a benzene ring, but you don't have a ring at all, so it's not going to be alicyclic. Following are aromatic. Aromatic must contain at least one benzene ring. Here I've got two rings fused together. The ring on the left has alternating double and single bonds. It is a benzene ring, so that's going to be aromatic. Here I've got two benzene rings. It's going to be aromatic. Here I've drawn it out in structural formula, but if I were to draw it out skeletal, I'd have a CH3, a C, a CH2, a CH3, carbon double bond to oxygen. This is what it would look like. No benzene ring in sight, not aromatic. Which of the following compounds are branched? If it's got a branch, then not all of the carbons are just in one long chain. So the first one, I've got structural formula. Again, I'm going to draw this out skeletal. So I've got a CH3, a CH, and a CH2, then a CHO. And on that second CH, I have got a branch. Okay, so this is what this would look like drawn out in full. And as you can see, you do have a branch. So I'm going to give it a tick. The next one, I've got no branches. It's just one long chain. So it's not branched. And the last one here, you can see the branch coming off the ring. That makes it branched. Which of the following are aliphatic and alicyclic? So this one here, it's not aromatic. There's no benzene ring, which makes it aliphatic. And I do have a ring, which makes it both. The next one, no benzene ring. So it is aliphatic, but they're not in a ring. So therefore, it cannot be alicyclic. Here, I have two ring structures, but as you can see, one of them is benzene. That means it's not aliphatic, and it's not alicyclic. Any benzene ring, it just immediately becomes aromatic, and you don't define it as anything else. Which of the following are aliphatic and branched? So this does not have a benzene ring, so it's aliphatic. It does have a branch. This does not have a benzene ring, so it's aliphatic, but there is no branch. This does have a benzene ring, so it cannot be aliphatic, even though it is branched. Which of the following are aromatic and branched? Here I've got a ring, but I've only got two double bonds. I don't have the three, so it is not aromatic. This one, this is a benzene ring, and it's got a branch. Here, no benzene rings in sight, so it's not going to be aromatic. Aliphatic and saturated. So this does count as being aliphatic because there's no benzene ring. It also counts as being saturated because you've got no carbon-carbon double bonds. Here, it is aliphatic because there's no benzene ring. And it is saturated because you've got that carbon-carbon double bond. Oh no, sorry, it's unsaturated because you've got the carbon-carbon double bond, therefore it doesn't fit the criteria. And here at the end, it is aliphatic. There are no carbon-carbon double bonds, therefore it is saturated. Which of the following contain the alcohol functional group? The alcohol functional group is an OH, but be careful here, okay? It has to be just the OH on a carbon by itself. In the first molecule that I've got, yes, I do have an OH, but that OH is on the same carbon as a double bond O. This means that this whole functional group is what we call a carboxyl functional group. It is not an alcohol, it's a carboxylic acid, so I'm going to put a cross next to 11A. In 11B, you've got an OH bonded to a carbon, but the double bond O is on the adjacent carbon. Here, they're both on the same carbon. Here, they're on adjacent carbons. That means you've got two separate functional groups. You have got an alcohol and you have got a ketone. Because I've got an alcohol, I'm going to give that one a tick. Here, again, that OH is on a carbon that's not bonded to anything else. That makes it an alcohol. You've also got another functional group here at the end, which I don't think we've looked at yet, which is called an amide. But as long as it's got an alcohol, I can give it a tick. So this one has split on me a little bit, so I'm going to push this down. Sorry. Which of the following compounds contain the carboxylic acid functional group? Okay, so to be a carboxylic acid, it's like what I had above. The carbon, double bond oxygen, and the OH all have to be on the same carbon. If I look at my first example, I've got a carbon double bond oxygen. Okay, I've got two of them actually, but the OH is not on the same carbon. The OH would need to be there, or there to make a carboxylic acid functional group. So I'm going to put a cross next to that one. Here, the OH and the C double bond O are on the same carbon, so that is a carboxylic acid. Here, I've got a C double bond O, but instead of having an OH, I've got an NH2, which, as I said above, makes it an amide, and it is not a carboxylic acid. The next one, I'm looking for aldehydes. To be an aldehyde, you have to have a C double bond O at the end of the chain. Here, I've got a C double bond O, but it's in the middle of the chain, so it is not an aldehyde. Here, I've just got an OH. When I write it out like that structural formula, and I've just got OH, that tells me it's an alcohol. Here, I've got the C double bond O. It is at the end of the chain, so it is an aldehyde. And here in structural formula, the way you spot an aldehyde in structural formula is that CHO. If it's OH, it's an alcohol. If it's CHO, it's an aldehyde. So I do have an aldehyde there at the end. If I'm looking for a ketone, I need that C double bond O in the center. Just not at the end of the chain. Here, I've drawn it out in structural formula, but that CO there, if I draw this out in full, I've got a CH3, a CH2, a C, a CH2, a CH3. That third carbon there is bonded to an oxygen. In order to have all of the bonds, if I look at that carbon, it's bonded to 2 carbons on either side, and then it's just bonded to an oxygen. The fact that it's bonded to no hydrogens tells me that that bond must be double between carbon and oxygen, meaning I've got a carbonyl group. Not at the end of the chain, I do have a ketone. The next one here, you can see I've got that hydrogen on the oxygen. That tells me I don't have a double bond. You'll also see here I've got a hydrogen on the carbon. So if I were to draw this out in structural formula, in skeletal formula, I get CH3, CH, CH3, and that CH is also bonded to an OH, okay? So because you've got that that hydrogen on the carbon and on the oxygen, that tells you don't have a double bond between them. Instead of having a ketone, I've got an alcohol. At the end here, I've got that C double bond O, not at the end of the chain, so I do have a ketone. And then here, I've got that C double bond O, but you can see at the end, I've got a hydrogen. You need to have 2 carbons to be a ketone. Here, I'm bonded to 1 carbon and a hydrogen. It's an aldehyde. It is not a ketone. Esters, these are a harder functional group, and we're going to look at them in detail in year 13. To be an ester, you have to have a carbon double bonded to an oxygen, single bonded to an oxygen, that is then bonded to some sort of alkyl group. And by alkyl group, I just mean a carbon with hydrogens on it. So here I do have that C double bond O. I've got the oxygen, and the oxygen is bonded to an alkyl group, so it is indeed an ester. Here in structural formula, this is also an ester. That's how you would represent it. You've got a CH3, a CH2, a C, double bonded to an O, single bonded to an O, bonded to a CH3. So that is also an ester. Here, I've got a carbon double bonded to an oxygen, single bonded to an oxygen, and that oxygen is bonded to a benzene ring, but that still counts as being a hydrocarbon. So again, I've got another ester. All 3 of them are esters. In question 16, I asked you to circle and label all of the functional groups. This here, carbon double bond carbon, would be an alkene. Here, I have got a ketone because I've got a carbonyl group in the middle of the chain. And here, I have got an alcohol. Make sure you didn't label that as a carboxylic acid. The OH and the double bond O are on separate carbons. That makes it a ketone and an alcohol, not a carboxylic acid. The next one, I've got a carbonyl group here at the end of the chain. That makes it an aldehyde. Next, I've got another carbonyl group, but this time it's in the middle of a chain, which makes it a ketone. I've got a chlorine here. This makes it a haloalkane. So if I had any of the halogens, chlorine, bromine, fluorine, any of them, bonded to a carbon, it makes it a haloalkane. You could also call it a chloroalkane to be a little bit more specific. Here, carbon double bond carbon, that is an alkene. And then here, I've got my carbon double bond oxygen, and I've got my OH. Above, I labeled this as ketone and alcohol because they were on different carbons. But here, because they're both on the same carbon, then all of this becomes one functional group, and it is a carboxylic acid. In the next one, again, I've got an OH and a C double bond O on the same carbon, which means I've got another carboxylic acid. I've got an OH on a carbon that is not bonded to anything else of significance, so that's going to be an alcohol. I've got a C double bond O. Again, that carbon's just bonded to 2 carbons on either side, which is going to make it a ketone. And then here I've got a carbon double bonded to an oxygen, that's single bonded to an oxygen, that is then bonded to this whole other group. This whole thing here is going to be an ester. Now we move on to naming. Name the following alkanes. So when you're naming, you need to count the longest continuous chain. So when you're naming from structural formula, again, I would recommend just drawing it out. It will make it easier to see. So I'm going to draw this here above. I've got a CH3 bonded to a CH2, bonded to a CH and a CH3. On that third carbon there, I have got a branch. My longest continuous chain is 1, 2, 3, 4 carbons long. Okay, if I go here, 1, 2, 3, 4, I can't get longer than 4. Okay, that means it's going to be butane, but I've got a substituent. If I number from left to right, I'm going to get 1, 2, 3. Carbon 3 has a substituent, but I number from right to left, it's carbon 2 that has a substituent. I always want to give the lowest numbers to my substituent, so I'm going to number it from right to left. On carbon 2, my substituent is a methyl group, so it's going to be 2. I'm not going to be able to put this in now. It is going to be 2-methyl butane. The next one up, something similar, and I've already drawn this out for you. You've got another branch here, all right? But again, the first thing you need to do is find your longest chain, okay? The instinct is just to assume that this is your longest chain, but it might not be. And if we count, we'll see that you got 1, 2, 3, 4 carbons if you just go from left to right. But if I move down the chain, I get 1, 2, 3, 4, 5 carbons. So by moving down the chain, I've got a longer chain. So it's not going to be butane, it's actually going to be pentane, because I've got 5 carbons in a row. It doesn't matter which way I count them. I can go 1, 2, 3, 4, 5 or 1, 2, 3, 4, 5. Either way, you're going to have your substituent on carbon 3. And again, that that substituent is a methyl group. So it's going to be 3-methyl pentane. This next one here looks a little bit more complicated. Again, you need to make sure where your longest chain is before you start naming. If I just go from left to right, I get 1, 2, 3, 4, 5, 6, 7, 8 carbons. If I try and go a few other ways, 1, 2, 3, 4, 5, 6, that's not longer. 1, 2, 3, 4, that's not longer. 1, 2, 3, 4, 5, 6, 7, okay? But I'm not getting any longer than 8. So just going from left to right gives me 8 carbons. So that's going to be octane. Now I need to know, do I go from left to right or right to left? If I go from left to right, my first substituent is on carbon 1, 2, 3. If I go from right to left, my first substituent is on carbon 1, 2, 3. Okay, so there's nothing to choose there. But if I go left to right, 1, 2, my second substituent is on carbon 4, so I'd have 3 and 4, but going this way, I've got 3 and 5. So I want to give the lowest possible number suited to my substituents. I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. I've got 3 substituents. On carbon 3, I've got 2 methyl groups. Because it's 2 methyl groups, I'm going to be calling it dimethyl. On carbon number 4, I have got 2 carbon groups joined together. That makes it an ethyl group. Okay, so I've got dimethyl and I have got ethyl. When you are naming these substituents, you have to put them in alphabetical order. So you've got a methyl substituent and you've got an ethyl substituent. E comes before M, so you're going to put the ethyl substituent first. The ethyl substituent is on carbon 4, so sorry, it's going to be, I'm going to struggle to fit this all in, so I'm just going to write it above. It's going to be 4-ethyl. Then you've got 2 methyl groups. They're both on carbon 3. So it's going to be 3,3-dimethyl. And then it's going to be, oh no, wait, I've got a third one. Sorry. I've got 3 methyl groups. I've got 2 of them here on carbon 3. I've got a third one on carbon 6. So it's going to be 3,3,6 trimethyl octane. Okay, so on carbon 4, you've got an ethyl group. You've got 2 methyl groups in carbon 3, so that's 3,3. and I'm carbon 6, I've got a third methyl group. So that trimethyl tells me I've got 3 methyl groups, and the numbers tells me where I will find each of those methyl groups. When you are doing your naming, you're doing it alphabetically. So I'm comparing ethyl to methyl. Ethyl comes before methyl, therefore ethyl is named first, even though it's on carbon 4 compared to carbon 3. When I had it there as dimethyl, you're looking at the E versus the M, not the E versus the D for dimethyl. So the ethyl would still come first in that case. So that's naming of alkanes. I'm just going to rub this one out because next we're going to look at naming of alkenes. So to name the following alkenes, here I have got it just drawn in structural formula. I've got a CH2 bonded to a CH bonded to a CH3. My double bond will be there. I've got 3 carbons, which means it's going to be prop. Because it's an alkene, it's going to be propene. Now, if you call this prop-1-ene, that is fine. But if I move the double bond to the other side, it would still be prop-1-ene, so the 1 is not strictly necessary. However, if you said prop-1-ene, that is fine. If I look here at the next one, again, I'm going to draw this out for myself. I've got a CH3 bonded to a CH, bonded to a CH2, a CH2, a CH, and a CH2. On that second carbon, I have got a CH3 group. And then down here at the end, you can see that I'm ending in a CH2 and a CH, which tells me that I have got a double bond there at the end. All right. First thing I'm going to do is count my longest chain. 1, 2, 3, 4, 5, 6. All right. There's no other way. 1, 2, 3, 4, 5, 6. That's going to make it longer than 6. So it's going to be hex. And when I am numbering, I need to give the lowest possible number to the double bond. So yes, I've got a substituent, but the double bond takes priority. And if I go from left to right, my double bond is starting on carbon 5. But if I go from right to left, my double bond is starting on carbon 1. So I'm going to go right to left. It's going to make it hex 1-ene. I do need to put the 1 in this time. It's always the carbon that the double bond starts on. So it's hex 1-ene. This would be carbon 1, 2, 3, 4, 5, and 6, and you can see on carbon 5 you've got a methyl group, so it's going to be 5 methyl hex 1-ene. The next one I've already drawn it out for you. Similar idea. Start by finding your longest chain. 1, 2, 3, 4, 5, 6. Again, it's not going to be any longer than 6 no matter which way you go. Again, I need to give priority to my double bond, so I'm just going to start labeling from right to left. It's going to be hex 1-ene again, but this time your methyl group is on carbon number 4 instead of carbon number 5. So it's going to be 4 methyl hex 1-ene. Next up, I have got haloalkanes. Name the following haloalkanes. So it's a haloalkane if you've got some sort of halogen there. Again, I'm just going to draw this out for myself, as I always do. I've got a CH3 bonded to a CH2, bonded to a CH, which has a Cl on it, bonded to a CH2, bonded to a CH3. So that's what it's going to look like, okay? That chlorine is in group 7. Halogens can only form 1 bond. So I know that that chlorine is not part of the chain, even though it's not in a bracket. I know it's a substituent. It cannot be in the middle of the chain because halogens can only form 1 bond. So if I look at the length of my chain, I've got 5 carbons. It doesn't matter if I go left to right or right to left. That chlorine is going to be on carbon number 3. So it's going to be 3-chloropentane. The next one, again, if I number my chain, 1, 2, 3, 4, 5. Okay, can't make it any longer than 5. If I go from left to right, my substituents are on carbons 2 and 3. If I go right to left, my substituents are on 3 and 4. So I'm going to go left to right and go 1, 2, 3, 4, 5. I've got chlorine on 2, I've got bromine on 3, but B comes before C in the alphabet. So when I'm naming this, I'm doing it alphabetically. And I'm going to go 3 bromo, 2 chloro, and because you've got 5 carbons in a row, pentane. 3 bromo, 2 chloro, pentane. Next one up, my longest chain is 1, 2, 3, 4, 5, 6, 7. Okay, and if I number left to right, I get the lower number on my substituent. So I'm going to go 1, 2, 3, 4, 5, 6, 7. Bromine again comes before chlorine alphabetically. So I'm going to start this off by saying that it's 5 bromo. And if I look at my chlorines, I've got 3 of them in total. 2 of them are on carbon 2. The third is on carbon 3. So it's going to be 2, 2, 3. trichloroheptane. There's 7 carbons, which makes it heptane. So 5-bromo, 2,2,3 trichloroheptane. Underneath, asked to name the following alcohols. First one is pretty straightforward. The first one, you've got 1, 2, 3, 4, 5 carbons in your chain. You want to give the lowest number to the OH, so I'm going to number from left to right, which puts that OH on carbon number 2. So because it's an alcohol, 1, 2, 3, 4, 5, because it's an alcohol, it's going to end in -ol, and it's going to be pent-an 1-ol. Sorry, no it's not, it's going to be pent-an 2-ol. You have to give the number that the OH is on because it could be on any of the carbons in this molecule. So pent-an 2-ol. Just look at where I split it up because a lot of you in the exam I think we're doing pent 2-ol. You need to have that AN, so it's pent-an 2-ol. In the next one, you've got CH3, CH2OH. You've only got 2 carbons. You've got your OH at the end. That is just going to be ethanol. In this case, I don't need to specify which carbon the OH is on because I'm always going to number that as carbon number 1. Okay, if I draw it for you, you've got CH3, CH2OH. If I have it on this carbon, I'm going to call this carbon number 1. If I put it on the other side, I would call that carbon number 1. So it's always going to be ethan 1-ol because it can only be ethan 1-ol. You just call it ethanol instead. Next up, I've got a chain. It's 1, 2, 3, 4, 5, 6 carbons long. As you can see, I've got 2 substituents. I've got a methyl group and I've got an OH. OH takes priority. So I'm going to number from left to right, not from right to left, because OH is more important than the methyl group. Bearing that in mind, if I'm naming this, I've got carbon 1, 2, 3, 4, 5, 6. On carbon 5, I've got a methyl group, so it's going to be 5-methyl. 6 carbons in total, so it's going to be hexan. And my actual alcohol group is on carbon 3, so it's 5-methyl, hexan 3-ol. Name the following aldehydes. Aldehydes end in al. Here I've just got 4 carbons, and it's going to be butanal. With aldehydes, you don't need to specify where the C double bond O goes because it has to be at the end of the chain and it's always going to be on carbon number 1. So you don't need to specify. It's just going to be butanal. Here, I'm going to draw this one out. You have got a CH3, a CH2, a CH, CHO. And on that third carbon there, you've got a CH3 group. Okay, so again, because this has to be carbon number 1, I'm going to number from right to left, not from left to right. Okay, so this is going to be carbon 1, 2, 3, 4. That means on carbon 2, I've got a substituent. It's a methyl group. 2-methyl, butanal. Again, no need for a number. Here, I've got 1, 2, 3, 4. Oh Christ, no! What am I doing? I'm doing the exact thing I told you not to do. Okay, with your aldehydes again, this has to be carbon number 1. So I'm going to go 1, 2, 3, 4, and 5. Has to be carbon number 1. So even though I've got a substituent over here, I number from right to left, not left to right. Priority goes to your carbonyl carbon. It's going to be pentanal, and on carbon 4, you have got 2 methyl groups. So it's going to be 4, 4 dimethyl pentanal. 4, 4 dimethyl pentanal. I'm just going to push this down. Oh God, almost there. Almost there. Yeah, kind of. Name the following ketones this time. So here I have got 1, 2, 3, 4 carbons. If I were to draw that out. Stop it. Sorry. If I were to draw it, I have CH3, a CH2, a C, and a CH3. The double bond O would be there. You always give the lowest possible number to my carbonyl group, so I'm going to number from right to left, and that makes it butanone. Again, in this case, I don't actually need the number, because if I were to move it to carbon 3, then I would number from left to right, and it would be carbon 2. If I put it on carbon 1 or 4, then it wouldn't be a ketone at all, it would be an aldehyde, so I don't need to have the number. If you wrote it as butan-2-one, that is absolutely fine. Next one up though, I do need to include the number because I've got 5 carbons and it could be a ketone on carbon 2 or a ketone on carbon 3. So in this case, I need to include that number and it's pentan 3-one. A lot of you on the exam, when you were naming ketones, were just calling it pent-3-one. You need to have that AN, okay? Just like we had with the alcohol, the aldehyde, it's pent-an-3-one. And just be aware of where you should split that. If I was splitting buth-an-one, I would split it between the AN and the O&E. That's where I'd put my number. Here, again, I'm going to count my longest chain, which is going to be 1, 2, 3, 4, 5, 6, 7. I need to give priority to my ketone, so I'm going to number from this side. 3, 5, 6, 7. I've got 2 methyl groups, I've got a bromine, and I've got a chlorine. Again, when I'm doing these substituents, it's going to be alphabetical order. Bromine is first, then chlorine, then methyl. So I'm going to have 6 bromo, 5 chloro, and on carbon 4, I've got 2 methyl groups. 4, 4 dimethyl. So 6 bromo, 5 chloro, 4, 4 dimethyl, and it is heptan 2-one. So I need to specify on which carbon I'm putting my carbonyl group in heptanone. So it's going to be heptan 2-one. So 6 bromo, 5 chloro, 4, 4 dimethyl, heptan 2-one. 23. Name the following carboxylic acids. The first one is straightforward. 1, 2, 3, 4. It's just going to be buthanoic acid. You don't need to specify on which carbon the carboxylic acid is, because it's always at the end of the chain, and it's always going to be carbon number 1. Okay, carboxylic acid carbon, always carbon number 1. So if I draw out the next one, I've got a CH3, a CH, a CH2, so it's going to look like this, and I've got a substituent here on carbon number over here. All right. The temptation might be to go from left to right to give the lowest number to your substituent, but you have to make your carboxylic acid carbon carbon number 1, which puts the methyl group on carbon number 3. So you've got 3 methyl buthanoic acid. Again, don't need to number where that carboxylic acid group, it goes without saying that it's carbon number 1. Likewise, over here, I've got 1, 2, 3, 4, 5, or 4, 5. So it doesn't matter which way I go, I'm always going to get 5 carbons in my longest chain. I've got a methyl substituent here on carbon 2. I've got an ethyl substituent here on carbon 3. Alphabetically, ethyl comes before methyl, so it's going to be 3 ethyl, 2 methyl, and it's 5 carbons in total, so it's going to be pent-anoic acid. Right, we're finished naming. The next one, write the molecular formula and the empirical formula for the following compounds. All right, so if I ask you for molecular formula, that is just asking you how many atoms do you have and how many of each type. So if I look at my benzene ring here, all right, I have got, if I were to fill in my skeletal formula, I'd have 1, 2, 3, 4, 5. I would have 6 carbons, so it's going to be C6. If I look at how many hydrogens I've got, each carbon already has 3 bonds to it, which means there is only room for 1 hydrogen on each of those carbons. So I'm going to end up with C6H6 as the molecular formula. The empirical formula is the simplest ratio. So if I've got 6 carbons and 6 hydrogens, that's not the simplest ratio. The simplest ratio would just be CH. I can divide across by 6 and get CH. For the next one, again, I'm going to start by counting my carbons. So I've got 1, 2, 3, 4, 5. So I'm going to start off with C5. Then I always put the hydrogens next. I'm going to have 3 on the first carbon, and 2 is 5, and 2 is 7, and 2 is 9, and 1 is 10. So I'm going to have C5, H10. And the only other atoms I have present are oxygen, and I've got 2 of them. It's common convention to go carbon, hydrogen, oxygen in that order, okay? But you're not going to lose marks for it as long as you've got the right number of atoms. But that is how you do it. It's carbon, then hydrogen, then oxygen. That's the molecular formula. Can I simplify that? I've got 5, 10, and 2. Is there a number that divides evenly into 5, 10, and 2? The answer is no. I can't simplify that any further. So the molecular formula and the empirical formula are going to be the same. The next one I look at, I'm going to start with my carbons yet again. I've got 5 carbons in my ring. There's carbon number 6, 7, 8, 9, 10. So I've got 10 carbons in total. Counting hydrogens, I would have only one hydrogen here because carbon's already got 3 bonds to it. So I've got 1 there. I'm going to have 2 there, which is 3, and 2 is 5, and 2 is 7. There's no room for a hydrogen here because carbon's already got 4 bonds. So I've got, oh Christ. So I've got, wait, how many just say ahead? I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, none there, 10, 11, 12, 13, 14, 15, 16 hydrogens in total. And then at the end, I've got 2 oxygens. So I've got C10H16O2 as the molecular formula. Can I divide across by any number to simplify this? The answer is yes. The number 2 divides evenly into everything. If I divide across by 2, I'm going to get C5, I'm going to get H8, and I'm going to get O. So that's the molecular, and that is the empirical. The next one, I've given you structural. I've asked you for skeletal. So you're going to have to draw out the skeletal. I've got a CH3. I've got a CH2. Then I've got a C, OO, CH2, CH3. Now, okay, to be fair, I've obviously got practice in this. But that COO, when you see it as COO, that is an ester. And what that's going to look like is carbon double bonded to an oxygen, single bonded to an oxygen, and then you've got the carbons on either side. Okay, you will become more familiar with ester functional groups, especially in year 13 when we study them in a lot more detail. Okay, the next one, I've got a CH3, I've got a CH2, then I've got a carbon. On that carbon, I've got a CH3 and I've got a Cl, and then I've got a CH2, and then I've got a C. And when it's HO like that, I know I've got an aldehyde. Okay, so to be fair, in true skeletal formula, I really shouldn't be including a hydrogen there at all, so I should just leave it blank, but they won't penalise you for the aldehyde. But this is what your skeletal formula should look like. And then the last one, I've got CH3COOH. If you see that COOH, that is a carboxylic acid. So it's going to look like this. So I've got 2 carbons, double bonded to an oxygen, bonded to an OH. All right. Now we're going to go from skeletal to structural, so the opposite. I'm going to put all of my substituents in brackets. I think it makes it easier to see. You don't technically have to do that, but I think it does help. So here, the first thing I've got at the end of my chain, I've got a CH3, and then I'm going to come along to a CH that is bonded to a CH3 substituent. Then I've got a CH2. Then I've got another CH that has a CH3 substituent. And then at the end of my chain, I've got a CH3. So that's going to be the first one. For B, I've got a CH3 bonded to a CH2. To represent that I've got a ketone, I don't need to use a bracket. I can just write CO. And then I've got CH2 and a CH3. Here for C, I've got a CH3 at the end, bonded to a CH2. Then I've got a CH that has a CH3 substituent, so I'm going to put that in a bracket. Then I've got a CH2, and then at the end, I've got an aldehyde, and to represent an aldehyde, I have to write it as CHO. If you put those atoms in different orders, you are wrong. An aldehyde has to be represented as CHO. The last one, here I've got a CH3, then I've got a carbon, a CH, that's bonded to a bromine. I'm going to put it in a bracket. Technically, you don't have to. Then I've got a CH2. And then at the end, I've got a carboxylic acid group, which is represented as COOH. Again, there's no other way to write that. It has to be COOH at the end. The next bit, draw the displayed formula of the following. I mean, displayed is a pain. If you're writing displayed, you have to show every atom and every bond. So it has to be carbon bonded to a carbon, bonded to a carbon, bonded to a carbon, bonded to a carbon, bonded to a carbon. So, oh Christ. I have to show all of my carbons there. I'll have to put in my alternating double and single bonds, and then on each carbon I will have to show that I've got a hydrogen. So you should be showing every single atom, taking no shortcuts. The next one, you're going to have carbon bonded to carbon, bonded to carbon, bonded to carbon, bonded to carbon, bonded to carbon. And then off this carbon, I've got a carbon, and a carbon. You don't need to draw it in a zigzag when you're doing this. And then I need to fill in all my hydrogens. So, oh no, wait, I've got a double bond there. So I've got 1 hydrogen on my top carbon. I've got 2 there. I've got 2 there. I've got 2 there. Here I've got none. There's no room. I've already got 4 bonds. Here I've got 2, 1 and 2. Here I've got 2, 1 and 2. Here I've got room for 1, 2, 3. Okay, so that would be displayed. The last one, I've got a carbon, double bonded to a carbon, single bonded to a carbon, single bonded to a carbon, that's bonded to a carbon. If I put in my hydrogens here, I've got room for 1 and 2 at the end. I've got room for just 1 here. This carbon here is going to have 2 hydrogens on it. This carbon here is only going to have 1 hydrogen on it. This one here at the end will have all 3. And then this carbon is also bonded to a CH2, CH3. So I'm being a little bit lazy there, but just scribbling that in. CH2, CH3. Technically, you should draw that out in full and show the bonds between those carbons and those hydrogens. We're almost there. All right, 28. So I'm moving away from naming and formulas, and we're going to be looking at curly arrows. Assign partial charges to each of the following polar bonds using electronegativity values to help you. So we've looked at electronegativity. We said it's the ability of an atom to attract electrons in a covalent bond. Chlorine is more electronegative than hydrogen. So in that covalent bond, that shared pair of electrons is going to be closer to chlorine. That means that chlorine does not have a full negative charge, but what we say a partial negative charge, which I represent by delta negative and delta positive. Between carbon and fluorine, fluorine is your more electronegative, so I'm going to have delta negative and delta positive. Between oxygen and hydrogen, oxygen's more electronegative, delta negative, delta positive, and then here, delta negative, delta positive, okay? Oxygen, fluorine, and nitrogen, they're your 3 most electronegative atoms. They're always going to have a greater share of the electrons. Chlorine is relatively electronegative as well, but you'll find those values in the table. Here I've written the curly arrows show the movement of a pair of electrons. In heterolytic fission, covalent bond breaks and both electrons go to the atom that has a delta negative charge. Draw curly arrows to show the heterolytic fission of the following bonds. All right. So I've started by putting the partial charges for you. So when you're drawing your arrows, and I am a real stickler for this, so I will mark you down if you don't do it right. But you have to start your arrow in the middle of the bond, and you have to end your arrow specifically on the atom with the delta negative charge. All right. So for example, in the next one, if it was just a bit vague, so if I started here, but my arrow ended out there, like you would not get the mark for that. It's not specifically ending on the atom with the, oh actually I've gone the wrong way, but with the charge. Similarly, if you didn't start it specifically at the bond, if you kind of did something that looked like that, okay, you're not starting at the bond, you're not going to get the marks for that. So you always have to start your arrow at a pair of electrons, which is the covalent bond, and you'll end your arrow specifically at the atom that's going to take those electrons, and it's always going to be the delta negative atom that will take the electrons. So on the other side, if I fill in my charges, I've got delta positive, delta negative, delta positive, delta negative, delta negative, delta positive. Again, look up those values if you're not sure. The more electronegative is going to get the delta negative sign. So here, starting at the bond, going to the delta negative. Here, starting at the bond, going to the delta negative. Here, starting in the bond, going to the delta negative. All right, just make sure those arrows are really tight and they're not just ending or starting anywhere vague. Last bit, curly arrows must always start either on a covalent bond, which is what we did up here, or on a lone pair or on a negative charge. Remember, curly arrows is the movement of a pair of electrons. They have to start on a pair of electrons. So a covalent bond is a pair of electrons, a lone pair is a pair of electrons, a negative charge represents a pair of electrons. So you're going to start on one of those 3 places. They always end on a positive ion or an atom with a delta positive charge. They're going to end on something that does not have electrons, and that's going to be represented by either a positive or delta positive charge. Draw a curly arrow to the movement of the electron pairs in the example first one's been done for you. So here I'm starting my arrow specifically on a lone pair and I'm ending it at a H+. This is telling me that the electrons move from this pair, okay, to form a bond between something that has electrons and something that does not have electrons. And we'll look at the products of these reactions later. At the moment, I'd be happy if you can just draw for me proper, why is it not working? I'd be happy if you can just draw for me proper arrows. So for the next one, I'm starting again on my lone pair and I'm ending at my H+, okay? Make sure there's nothing vague about it. Start specifically on the lone pair, end specifically on the H+. The next one, I said I can also start it on a negative charge. So I'm going to start this time on the negative charge. I don't have anything positive, but I do have something delta positive. So that is where the arrow is going to end, starting the negative charge, ending on the delta positive carbon. And then the last one, okay, I've got 2 lone pairs here. It doesn't matter which lone pair I actually start on, so I'm just going to pick one. And I've got, doesn't matter which lone pair I start on as long as I start on one of them. And again, I don't have anything positive, but I have something delta positive, so that is where my arrow is going to end. So I'm starting on a pair of electrons, a lone pair, covalent bond, a negative charge, and I'm ending always at something positive or something delta positive. You've got the movement of a pair of electrons from an area of high electron density to an area of low electron density. Okay, so I know this video is very long and there's quite a lot of information there. If you've got any questions on any of it, then I'm not going to see you for the next, 3 weeks. So you've got so much time to get your head around everything in this video and to message me and ask me questions if anything is still confusing. When I see you guys again, I am going to be giving you like 15 to 20 marks, I haven't decided yet, on this stuff. Some of the definitions, drawing curly arrows, naming, the difference between molecular, empirical, structural, skeletal formula, all of it. It's really, really important that you get a good grasp on it because it comes up in every single chapter that we're going to study for the next 2 years. So any questions on any of it, ask me. I do expect you to come back being really comfortable with all of this content. So if you need help, let me know. But if I don't hear from you, I'm just going to assume that everyone is comfortable with this content, and you will get a detention when I see you again if you can't answer my the questions that I give you at the start of next term. Okay, Merry Christmas.